Hello friends, welcome to Grade Up. My name is Rohan Patil and I am here to spark up your preparation with your plan Sparkup JE’19. Now today's we are continuing with the last lecture of microprocessor. In the last lecture we have studied the architecture of the microprocessor 8085 as well as the pin diagram as well as the basic machine cycles of the microprocessor, which were opcode fetch, memory read as well as memory write. So in the today's session we will be continuing to that part. If you have not attended the previous lecture, please go to the previous lecture, because in this lecture you will require most of the part from the last lecture. So let's continue with our today's session. That will be the basic instructions in the microprocessor. So in the today's lecture we will be continuing with the arithmetic instruction. As everyone knows that there are some basic arithmetic operations which are addition, subtraction, multiplication, division. These are the basic arithmetic operations. So in the today's lecture we are going to see which are the arithmetic operations possible in the microprocessor and how they are performed inside the microprocessor. So let's begin the today's session. So we are here we will have our first instruction as add R. So in the last lecture we have seen that this is our basic microprocessor and this is this is our microprocessor and this is our memory. So in the memory, different memory blocks are there. This is our memory and this is our microprocessor. They are connected with the bus. In the last lecture I have explained you what is bus and how they are connected. Suppose here it is written that add B. Suppose in the memory actually we won't be having a like this content. We will be having hex codes. In the RRB JE exam, hex codes are not in the syllabus, so don't try to remember the hex codes, but I have explained them here because it may happen that in future or in other exam you may require the hex codes. That's why I have written the hex code over here, so you can use them for different exams, but here they are not useful. So actually what happening here is actually add B is not written over here. Here it will be actually written 80, but as microprocessor is starting from this address, so it understood that this is a like instruction, this is not a data. Suppose in the next memory location it may possible that it is again 80, but microprocessor will understand the difference between the data and the opcode, because it will by default start from the opcode instruction only. So here you have written 80, so by 80 it will come to know that it's B. It is nothing but add B. So microprocessor will understand that you have to add the contents of B register with A register. So it will require memory fetch machine cycle. It will require memory fetch machine cycle. And in the last lecture I have explained you that memory fetch machine cycle requires 4 T states. So that means after 4 T states, this add B instruction will be decoded by this microprocessor, and it will come to know that it has to add the contents of B register with the accumulator. So the description of the instruction says that add register content to the accumulator. So it will, but you guys can see that both accumulator as well as the B register both are inside the microprocessor. So as soon as the microprocessor comes to know about the add B instruction, it immediately adds the content of the B register to the accumulator. So it will not require further any time. So after 4 T states, the content of the B register will be added to the accumulator. So this instruction require total I have given bytes, machine cycles as well as T states. So as you can see that it has occupied only one position in the this memory, so it is only 1 byte instruction. As it requires only memory fetch machine cycle, it requires only one machine cycle, as well as machine cycle requires 4 T states. So this instruction completes after 4 T states. And remember that if the arithmetic operation is simple addition, simple subtraction, then all flags will be affected. So what are the basic flags we have studied? So sign flag was there, 0, as well as auxiliary carry, parity, as well as carry. So these flags are present in the microprocessor, which I have explained in the previous lecture. So depending upon the result of this addition, add A plus B, and this will be stored in the accumulator again. So depending upon this result, these flags are affected. So this is how the add R or add any register operation happens inside the microprocessor. So let's begin with the next instruction. So in the next instruction we have subtract B. So it is same as that of the add. So it is just like that was addition operation, and it is subtraction operation. So in subtract R, what will happen? Suppose you have written subtract C over there. So accumulator, the contents of C register will be subtracted from the accumulator, and it will again stored back inside the accumulator. So similarly as the addition, it will require only one byte. It will require only one machine cycle, 4 T states, all flags will be affected, and the description of this instruction will be the contents of the register are subtracted from the accumulator. Be alert that it is A minus C, not C minus A. C minus A is not there, it's A minus C, and the result is stored back inside the accumulator. So this is how the subtract R instruction works. So let's move to the next instruction. So next instruction is add M. So in the previous lecture I have explained you what is M. Suppose we have address, we have HL register, in which suppose in H we have stored 20 and in L we have stored 30. And inside the memory also there are different memory locations are there. Actually it is, suppose it is a 16 address buses are connected to it, is 2 raised to 16, that is 64 KB. So this memory is 64 KB. So it has 64 memory locations, out of which some memory location will be 2030, where it is written 40. Suppose it is written 40. So what the microprocessor will do is, and suppose the microprocessor is running here now, and it has written add M. There is a opcode for that also, hex code is 86. So 86 will be written here, and let the microprocessor is here. So it will come to know that it has to add M, and what is M is the memory location pointed by the HL register, that is 2030. So the contents of the 2030 will be added to the accumulator. So accumulator will be accumulator plus the contents of the memory location 2030, that will be A, plus 40 will be the contents of the accumulator after its execution. So what happens here is, first, as you have seen that opcode fetch is there. First opcode fetch will be there as usual, opcode fetch. First memory cycle will be opcode fetch, as well as it requires also the contents of the memory location 2030. So it will require one more machine cycle, that it has to read the contents of the memory location this. So it will also require a machine cycle called memory read. So it will require 2 machine cycles, opcode fetch as well as memory read. So let's do the analysis. So it can add the contents of the memory location pointed by HL pair to the accumulator. It requires add M. It requires only 1 byte. So it is a 1 byte instruction, but it required 2 machine cycles, which are opcode fetch and memory read, as well as it required 7 T states, because opcode fetch requires 4 and memory read requires 3 T states. I have explained this in the last lecture, why it requires 4 and why it requires 3. So total it will require 7 T states for its operation. And I have told you that if there is simple addition or subtraction, all the flags will be affected. So all the flags will be affected after the operation. So I guess you have understood this concept, because similar concept will be used in the next instruction, that will be subtract m. Here also the memory location where the pointed by the HL register like 2030, the contents of the memory location 2030 will be subtracted from the accumulator, and the result is again stored back to the accumulator. So it is same as the previous. So it was subtract m, so it requires only 1 byte, as well as it required 2 machine cycle opcode fetch as well as memory read. So it required 2 machine cycle. Opcode opcode fetch requires 4 T states, as well as memory read required 3 T states. So it will require 7 T states. And as I have said that it is a arithmetic instruction, so all flags will be affected. So you can remember in this way. So we will move to our next instruction, which is add immediately 8-bit data. So just remember that how it will be stored. So in the microprocessor, I am showing you the memory here, which is connected to the microprocessor. In the memory, here it will be written add immediately, and suppose it is written 20 here. So microprocessor have reached here. So what microprocessor will understand that this is basically means that add immediately. Add the immediate 8-bit data to the accumulator. That is, the immediate data after this instruction will be added to the accumulator. So what will result of instruction will be accumulator content will be added by 20. So suppose there is 30 stored in the accumulator first, then now we are adding 20. The contents of accumulator will now become 50. So it requires opcode fetch. First it will require opcode fetch. Opcode fetch will be the first. Opcode fetch will be the first machine cycle, as well as it has to read the contents again back to the memory. See, whenever you are reading from the memory or writing from the memory, you will require the corresponding machine cycle as memory read or memory write. So be alert that here it is opcode fetch, but here it is memory read. So opcode fetch as well as memory read. So 2 machine cycles will be required. It is a 2-byte instruction because it is requiring 2 spaces in the memory. So it is a 2-byte instruction, 2 machine cycles, and 7 T states are required, and all the flags are affected based upon the result of this. So it may happen that carry is generated or auxiliary carry. Suppose it happen that even parity is happening. So depending upon that, the corresponding flag will be affected. So let's move to the next instruction. Similarly, it is a subtract immediately 8-bit data. So this instruction will 8-bit data is subtracted from the contents of the accumulator, and the result is again stored back in the accumulator. Similarly, as the add instruction, it requires 2 bytes. It requires 2 machine cycles, which are opcode fetch as well as memory read, and they require 70 states, and all flags are affected based on the operation or the result of the operation. So it is same as the previous, just previously it was addition operation and now it is subtraction operation. So let's move to the next instruction, which is ADCR. What does it mean? See, it means that add the contents of the register, same as previously in the first instruction I have shown you, to the accumulator along with the carry. See, here the carry flag is also important because this carry flag is again added back. So it requires, similarly it requires only ADCR. Suppose we are adding the contents of D register here, so here it will be opcode hex code will be 8A. So whenever microprocessor reach here, it understood that it has to add the contents of D register to the accumulator. It has to add the contents of D register to the accumulator along with the carry. But as you can see that microprocessor has A register, D register as well as the flag register. So everything is inside the microprocessor. So this after the fetching of this, after the fetching of 8A, after the fetching of 8A, it will not require any further time. So this addition will be done after 4 T states. So it is a 1 byte instruction. It requires only 1 machine cycle, which is opcode fetch. So it required 4 T states, and all flags are affected based upon the result of the addition. So this is how ADC. See, this C indicates the carry, AD indicates the addition, and this R indicates the register on which you are going to perform the operation. So let's move to the next instruction, which is SBBR. The carry flag in the subtraction operation is also known as the borrow. So that's why this B comes into picture. This SB stands for subtraction and R. So what will happen is, suppose this is the accumulator. So accumulator minus the corresponding register, suppose E register, suppose corresponding E register as well as the carry flag is also subtracted. Carry flag is here called as the borrow flag. So the contents of the register and the borrow flag both are subtracted from the contents of the accumulator, and the result is stored inside the accumulator. As everyone till now understood, if you have understood till now everything, you must understood that it is a 1 byte instruction. It will require only 1 machine cycle, which is opcode fetch machine cycle, which require 4 T states, and all the flags will be affected depends upon the result of the operation. So this is how the SBBR instruction works. So let's move to the next instruction, which is ADC M. So what does it mean? I have told you M is the nothing but the memory location pointed by the HL pair. Suppose it is 4050. It is the memory location pointed by the HL register 4050, and here it is written 30, and till now your microprocessor is reached here, and here it is given 8E. So by 8E, it is the hex code of the ADC M. So by 8E, whenever microprocessor reach here, it comes to know that it has to add the content of the memory location along with the carry to the accumulator. Sorry. So the constraint of the contents of the accumulator after its execution will be the accumulator as well as the contents of the memory location 4050, which is 30, and as well as it will add the carry flag. So initially it was add M. We have understood the add M. Similarly, it is only C is extra, so we are adding carry extra. So this is the instruction where you are going to see the result in this way. And as it is arithmetic, simple arithmetic operation of addition, all the flags will be affected based upon the result of the addition. So let's move to the next instruction, which is SBBM. So similar as that of our previous instruction ADCM, this is the SBBM instruction. So it will also same, it will require, it is only 1 byte instruction, 2 machine cycles which are opcode fetch, and memory read will be required. And what it will do is it will subtract the contents of memory location pointed by the HL pair along with the carry. It will subtract the contents of the HL register along with the carry. Carry here in the subtraction we call carry as a borrow. So what it will do is the contents of the memory location pointed by HL pair and the borrow flag are subtracted from the contents of the accumulator, and the result will be again stored back to the accumulator. See guys, from the instruction only you can understood what it is going to happen. So don't worry about the so many instructions. Just remember the thing that this M indicates the memory location pointed by the HL pair, this indicates the borrow, and this indicates the subtraction. So you will easily understood what it is going to do. Once you understood that what does it mean, then you can also calculate the how many byte instruction, because you can easily write SBBM in a single memory location. It will be a 1 byte instruction. So M is pointed by HL register, so it will be somewhere here. So microprocessor again have to read this data, so it will surely require 2 machine cycles, which is opcode fetch and memory read, and it will 4 plus 3, so it will require 7 T states. So after watching an instruction, you can easily find out how many T states are going to require. Just you have to think a little bit. And as I have said that it is an arithmetic operation, all the flags are affected depending upon the result of the operation. Suppose in the accumulator it was previously 20 and the memory location pointed has 19, and as well as the carry flag was 1, so that the result will be 0. So 0 flag will be 1, sign flag will be 0 as it is a positive number, as well as parity flag will be 1 because it has even number of ones, and auxiliary carry will not be generated, carry will not be generated, so this will be 0. So in this way this instruction works. So I have explained you the detailed working of SBBM. I hope you will understand the previous instructions in this way, as well as the next instructions in the similar way. So let's begin with our next instruction. So our next instruction is ACI 8-bit data. So what this instruction is, suppose it has written that ACI, the hex code for this is CE, and it has given the 8-bit data 30. So what it will do is add the immediate 8-bit data to the accumulator. So it will add 30 to the accumulator. So the contents of the accumulator will be accumulator with 30 plus, as you can see that carry is here, so along with carry. So accumulator plus 30 plus carry, and it will require opcode fetch for this as well as memory read for this. So it will require 4 plus 3, that is 7 T states will be required, 2 machine cycles, as well as it have required 2 bytes of, it have consumed 2 bytes of memory. So it is a 2 bytes instruction. The description I have already explained, as well as is affect all the flags. So this is all about the ACI instruction. So let's move to the next instruction. Our next instruction is SBI 8-bit data. It is same as that of the add instruction. Instead of add, it is subtract. So subtract, C, this I indicate immediate 8-bit data, this B indicates with borrow, and this S indicates subtraction. So the contents of accumulator with the corresponding register, suppose D as well as carry. So this is going to happen. So let's see the 8 bits of the data. The data, suppose it has given 20, suppose it has 12 is the data. The 8 bits of the data and the borrow flag, so carry here is called as the borrow, are subtracted from the accumulator, and the results are stored in the accumulator. So say as that of previous instructions only, it is a 2 byte instruction, because here it will require 1 byte, and this 1 byte and this data will require another byte. So it is a 2 byte instruction. Opcode fetch, memory read, so 4 plus 3 is 7. So it is a 2 byte instruction. It requires 2 machine cycles, which requires 7 T states, and all the flags are affected depending upon the operation. Sorry. So let's begin with the next instruction, which we have as INR. Basically INR is the short form of the increment. So you can remember in this way, this is INR. So increment R. So it is going to increment the contents of the respective registers. So what are the possible registers you can do here is A, B, C, D, E, H and L. So suppose you have to suppose you have to increment the contents of the accumulator by just 1. So either you can do that add immediately 0 1 H, but it will, you can understood that it will require 4 T states, 3 T states, so 7 T states will be required for the simple increment. So the another instruction to do this we have is INR R. So here and the corresponding hex codes are there. It will be stored in the memory as this thing, suppose 1C. So it will increment the content of E register. C, first opcode fetch will happen, and it will understood that after 1C it will understood that it have to increment the content of the register E by 1. As you know that this is the microprocessor and this E register is inside the microprocessor. It just have to add 1 to E, which is already inside the microprocessor. So it will not take any further time. So after opcode fetch, the E register will be incremented by 1. So it is a 1 byte instruction. It requires only 1 machine cycle and it requires 4 T states. But be alert about here. In the addition and subtraction, all the flags were going to affect, but in the increment operation, increment as well as decrement, carry flag is not affected. Be alert here, carry flag is not affected. Remaining sign, 0, parity, auxiliary carry, all the flags were affecting, but carry flag is not modified. So be alert when in the case of addition of a simple register, it is a 8-bit. See, it is different for the 8-bit registers and different for the 16-bit registers. For simple addition subtraction, all the flags were affected. For 8-bit increment, carry flag is not affected, but all other flags are affected. We will see later what happens to the 16-bit registers. So let's move to the next register. Similarly, decrement are the contents of the register indicated will be decremented by 1. The result is again stored back to the same register. It is a 1 byte instruction. It will require only 1 machine cycle with 4 T states. These are the corresponding hex codes, and similarly as that of increment, carry flag is not affected. So be alert that carry flag is not affected in increment and decrement operations. The content of the register are decremented by 1. So let's move to the next instruction, which is INRM. So here you have to be very careful. Suppose this is the memory. Here it is written that INRM. The hex code for this is 34. Sorry. So here 34 will be written. This is your microprocessor. So microprocessor is connected to the memory. Suppose the current execution is going from here. So microprocessor understood that 34, that is it has to increment the contents of the memory location pointed by the HL pair. HL pair is within the microprocessor. In HL pair, suppose HL, which is written as 2021. So this is the memory location 2021 where 30 is written. So increment, decrement, whatever addition, subtraction, whatever operations are possible, that are possible inside the microprocessor only. Microprocessor cannot do any operation directly on the memory. So what will happen? Let's see what is happening here. So it first come to understand that 34 is written here. So it have to add the contents of the memory location pointed by HL by incremented by 1, and result again same location it has to store. So basically this 31 should become 30 should become 31. So what will happen is first opcode fetch will be there. First opcode fetch will be there. So after opcode fetch, that is after 4 T states, it will have understood that what he has to microprocessor has to done. So it will read this 30 and it will store inside the temp resistance. And this is the temp resistance use. So in the yesterday's lecture we are not discussed about the uses of the temporary register. So this is the use of the temporary register. It is a 16-bit register, out of which one is used to store this 30. So 30 is stored here. So we have gone through a memory read, and once this 30 come inside the microprocessor, it is immediately stored in this temp register. So it required 3T. then it is incremented by 1. As I have explained you that in the microprocessor whatever is happening, it does not require any time, it is an instantaneous process. So it became 31, and now it is again, this is memory read and this is memory write. So it is again written back to the memory, so it will again require one more machine cycle, that is memory write, which again required 3 state. So total it required 10 T states. I hope you have understood this instruction. So let's revise what this instruction is doing. The contents of the memory location pointed by HL are incremented by 1, and the result is put in the memory location back again. So it is only 1 byte instruction, but it requires 3 T states of code fetch, memory read, memory write, and required 10 T states. C, as that of the similar, all the flags are affected except carry flag, because it is a 8-bit increment. I have explained you that 8-bit increment, whenever there is 8-bit increment, carry flag not affected, carry flag not affected. So carry flag is not affected. So let's move to the next instruction, which is decrement tab. This will happen same as that of the increment tab, just the opposite of the addition, subtraction will be happening. So I think that I don't have to explain the instruction once again. The contents of the memory location pointed by the HL pair will be decremented by 1, and the result will be again stored back to the memory location. It will be 1 byte instruction. It will require 3 T states, which will be again opcode fetch, memory read, decrement it, and again memory write. So it will require 10 T states, and similarly carry flag will not be affected. So I hope you all are clear till this instruction. So let's move to the next instruction, which is INX register pair. So what I have explained you that BC, DE, HL, SP, these are the registers, 16-bit register. So you have till now you have understood that how you can increment by 1 the contents of simple register like B register, C, that is 8-bit increment we have done. So now you are dealing with the 16-bit increment. So let's do it. The contents of the register pair, these are the valid register pairs, you can write over here, are incremented by 1 and stored in the register pair. The instruction views 2 registers as 16-bit number. I have explained you that B is 8-bit, C is 8-bit, but by combining them, these are the only valid pairs. You cannot combine C and D. You can combine only BC, DE, HL, and SP. Stack pointer is already a 16-bit register, so you can increment it also by 1 by using increment operation. These are the corresponding hex codes. But remember that what is happening here, B register is also there, C register is also there. So in the microprocessor, B is there, C is there, and here you have doing the opcode fetch. So here opcode fetch INX RP, suppose it has written INX B. So whenever X is there, it will require the 6 states. So the instructions, most of the instructions except one, which is XCHG. So except this instruction, wherever you find the X, remember that it requires 6 T states for opcode fetch only, because while opcode fetching, it will fetch the opcode as well as it will combine the register and then increment by it by 1. So this will require a little bit of time, so it will combinedly require 6 T states. But till now please understood that it is only 1 byte instruction. It will require only opcode fetch machine cycle, which requires 6 T states in this particular case. So remember that whenever X is there except this instruction, it will have the 60 states for its operation. So the contents of the register pair are incremented by 1, and it is a 1 byte instruction. It requires only one machine cycle, which is opcode fetch, and it requires 60 states. These are the valid register pairs, and no flags are affected. In case of simple 8-bit increment, carry flag was not affected, but in case of 16-bit increment, no flags are affected. No flags are affected. Be alert about here. No flags are affected in increment register pair. When we are going to increment the register pair, no flag is affected. So let's move to the next instruction, which is decrement register pair. So similar that of increment, decrement will be happening. So the contents of the register pair are decremented by 1 and again stored back to the register pair. The register pair is treated as a 16-bit number because each of this register is 8-bit except this. So combinedly they become the 16-bit. So out of that 16-bit, 1 is subtracted and again that is stored. This requires only 1 byte in the memory. It requires only one machine cycle, which is opcode fetch, and it requires 60 states for the opcode fetch. And as I have explained you that for 16-bit addition or subtraction, no flags are affected. No flags are affected. So be alert about this INX and DCX instructions. So no flags are affected. So let's move to the next instruction, which is compare R. See guys, this is basically same as that of the subtraction operation, but the result is not stored in the accumulator. Suppose suppose we have SUB-R. So suppose SUB-C register was there. So what we were going to do is we will A minus C operation is performed and the result is stored in the accumulator. But if you are given that CMPC, same operation will be performed, A minus C, all the flags will be affected. Flags will be affected. Flags will be affected, but the result is not stored back into the accumulator. The accumulator contents will remain as it is. Accumulator as it is. So be alert that accumulator contains as it is. Just the flags are affected due to this compare R instruction. So here you can observe that the contents of the register as compared to the contents of this register are compared to the accumulator. Both the contents are unaffected after this operation. A contents are unaffected, C contents are unaffected, and the following flags are show the result of comparison. So you can understood which is greater by this flags. If A is less than R, so if A is less than R, so it will definitely carry will be generated, and as they are not equal, 0 flag will not be generated. So 0 flag will be 0, but carry flag will be 1 because A is less than this R. Suppose A is equal to R. Suppose A has 20 and C has also 20. So 20 minus 20 will be 0. So 0 flag will be 1, but there will not be any generation of carry. Suppose A is greater than C. Suppose A is 30 and this is 20. So 30 minus 20, 10. So it is positive 10. So carry will not be generated as well as the result is non-zero. So similarly these flags are affected, as well as be alert that sign flag, parity flag, auxiliary carry flag are also affected based upon the result. So this instruction basically does what is A minus C, that was happening in SUB-C, but in CMPC, SUB-C, what was happening? A minus C, but in compare C, A minus C, that part is only not happening. All the registers are affecting depending upon the result. This I have explained you here. All the flags are affecting, but the contents of accumulator and the R register will not be affected. Just remember this part. This is the most crucial part in this instruction. This instruction is used to just compare the data, and according to that, what was the comparison, you can see that from the carry flag and zero flag, which was greater, equal to, or less, what was that, you can understood by this section. So let's move to the next instruction, which is compare M. So in the previous instruction, it will require only 1 byte. It is a 1 byte instruction. It will require only 1 machine cycle, and it requires 4 T states. I forgot to tell you that. So let's move to the next instruction, that was compare M. So here what was happening, the contents of the memory location pointed by HL pair. So this is HL 20, 21. This is your memory. This is your memory. This is 20, 21, and here you have written suppose 10. Your pointer is now here. Here it has come over BE. So from BE, the microprocessor has understood compare M. So what it will do is go to the memory location 2020, will read the data. So here it is opcode fetch as well as memory read. 4, 3, 7 T states will be required. It is a 1 byte instruction because only B is written, and it requires only 2 machine cycles, which is opcode fetch and memory read. So this 10 is compared with the accumulator, and the result is not stored back at that accumulator. See, subtraction will happen, all the flags will be affected according to that, but the result is not stored back to the accumulator. See, suppose the accumulator has 5, so 5 minus 10 will be minus 5, so carry will be generated, 0 flag will be 0. Suppose accumulator is 10 only, so 10 minus 10 is 0, so carry flag will be 0, but the 0 flag is 1 as the result is 0. Suppose if accumulator has 20, so 20 minus 10 is 10, which is positive, so carry will be 0 as well as 0 flag is also 0. So this is how compare M instruction works. So let's move to the next instruction, where we have compare immediately 8-bit data. So here it will be written as FE, and suppose here it is given 50, your accumulator has 20. So let's see what is happening. It will compare whenever, suppose the pointer of the accumulator is pointing here, so what we from FE it will understood that it have the compare. See, compare immediately, this immediate 8-bit data is compared with the accumulator, but accumulator data is greater than this. So first you will require opcode fetch as well as you required memory read. Now this 15 is now copied to the temporary register. So now in the microprocessor itself you have this accumulator content and this temporary register, so it will not require any further time. So after the memory read, that is after 70 states, the flags will be affected, but we know that in the compare operation the contents of the accumulator will not change, as well as the contents of the memory location will not change. So the 8-bit data is compared with the contents of the accumulator. The contents of the accumulator are unaffected. The flag distribution, flags, how the flags are affected I have given here, as well as the remaining flags are also affecting based upon the result. Be alert about this. So let's move to the next instruction, which is DA. So what do you understand by DA? So the DA is basically decimal adjust accumulator. So in the DA operation, what we check, suppose a number is given as 0, 1. So 0, 1, it is a 16-bit number, so it will be 0, 0, 0 and 0, 0, 0, 1. So it is a valid BCD, it is a valid BCD. So in the DA operation it is checked whether the given number is a valid BCD or not, and if it is not a valid BCD number, it is converted to the corresponding BCD number. I hope in the digital In the digital electronics, Abhishek sir must have explained you what is BCD numbers, but let me tell you, from 0 to 9, that is total 10 numbers are the only valid BCD numbers. After 9 we don't have valid BCD number. Suppose it is given as 0A, so that will 0, and this is A, this is 0, and A is basically 10 in the hexadecimal representation. So this is 10. This is not a valid BCD. So whenever it is not a valid BCD, 6 is added to the one invalid BCD number and it is made valid BCD. See what happening: 0, 1, 1, 0, 1, and again 1 is generated, 1, 1, 0, and 1. So this is the result. This is 4 and this is 1. So this is a valid BCD, this is a valid BCD. This operation is done by DA operation. So it will check what is stored in the accumulator. If it is valid BCD, then it's okay. If it is not a valid BCD, it will transfer it to the valid BCD. If this is valid, not valid, 6 is added. If both are not valid, 6 is added here also, 6 is added here also, and depending upon carry flag will be generated. That will not be an issue because all the flags will be affected based on the result. So this instruction will, obviously you can understood that once DA is understood by the microprocessor, accumulator is inside the microprocessor, so it can do whatever it want on the accumulator in just fraction of seconds. So it will not require any further time. So it will require only opcode fetch machine cycle. So it is a 1 byte instruction. Opcode fetch is there and it requires 4 T states. The contents of the accumulator are converted from a binary value to 4-bit binary coded decimal digit. So what has happened is it has converted the binary coded number to the valid BCD number. So this is how this works. So this is all about the DA instruction. So let's move to the next instruction, which is our DAD register pair. So DAD, this is the double addition. So AD, this D indicates double and AD indicates addition with register pair. So what are the valid registers pair are used here? See guys, in exam they may ask you what are the valid register pairs for the DAD instruction. So for any instruction, be alert about what are the register pairs or what are the registers can be used in that instruction. So here BC, DE, HL, SP, these are the valid register pairs, and the contents of the register pair, suppose you have given DAD B, so content of the BC will be added to the HL and stored back to the HL. So this operation is performed by this. The content of the register pair are added to the content of the register pair HL, and the source register pair is unchanged. BC contents will be unchanged, but the HL register contents will be added by the contents of the BC. See, let me tell you that how it is obtaining. So I have explained you, whenever X is there, 6 T states are required. Whenever X is there, 6 T states are required. But here what is happening, we will check that in the memory. Suppose it has given that DAD RP, suppose it is given 29. When the microprocessor reached here, it understood that 29 is here, and 29 indicates that add the contents of HL pair. See, by 29 you are going to add the contents of HL pair to HL pair again itself. The contents of HL pair will be basically multiplied by 2. Because HL will be HL plus HL. This is done by this 29. But it will first require one opcode fetch memory, opcode fetch machine cycle. So it will require 4 T states. Be alert that this opcode fetch required 4 T states. So it has understood that the microprocessor has understood that it has to add the contents of HL pair to the HL pair only. So basically it should not require any time. Till now I have explained you that if everything is with the microprocessor itself, it will not require any time. But here be alert that it is a 16-bit addition. This is a 16-bit number, this is a 16-bit number, and our microprocessor is a 8-bit microprocessor. In the last lecture I have explained you why this microprocessor is called as 8-bit microprocessor. So it is a 8-bit microprocessor. It cannot do 16-bit addition that easily, so it requires 6 more T states. This is a special type of instruction, so please in this instruction remember that it requires 6 more T states for the addition of the register pair, that is 16-bit number to the 16-bit number, and again to store the 16-bit number, and that will be bus ideal state. So the buses that are connected between the microprocessor and the memory, or the buses inside the microprocessor, are in the ideal storage state, so they will not be doing anything until this operation is performed. So this operation can be used to multiply the contents of HL register by 2, or add the contents of these register pairs to the HL pair. So this requires 2 machine cycles. This requires 2 machine cycles extra with 6 T states, 6 more T states. So this is a 1-byte instruction, because we will be writing only 29 or 39, whatever it is that will be written in the microprocessor. So it is a 1-byte instruction, but it required 3 machine cycles. I have explained you opcode fetch will be there, as well as 2 machine cycles extra, where bus will be in ideal state condition. So it required opcode fetch as well as 2 machine cycle extra, so it required 3 machine cycles. This opcode fetch requires 4 T states, and these 2 machine cycles required 6 more T states, so combinedly it requires 10 T states. This is a special instruction. You will not be having such difficult instructions further, so this is just a special instruction. In this case, remember that it required 10 T states and has 3 machine cycles. If the result is larger than 16-bit, carry flag is set, otherwise no flags are affected. Be alert that no flags are affected. It is same as INX, because it is also operating on 16-bit. Here also it is operating on 16-bit. Whenever we are operating on 16-bit, no flags are affected. But here, if the addition of these two, that is suppose if the contents of the HL register are suppose 10 10 10 and again 10, so this is the contents of HL. So after executing this DAD instruction, what will happen? This thing will be added to this thing. So 0 0 0 0 and 0 0 0 0, and this carry flag is generated. Then only carry flag is set. Otherwise, no flags are affected in this instruction. And so see, you guys can see that there are 8 zeros, but you can see that it will not affect the 0 flag, because it will only affect the carry flag. It will not affect the 0 flag or parity flag. In other cases it will affect 0 flag, because there are the result is 0 in the accumulator, the result is 0 in the HL pair, as well as the parity flag will not be also affected, even if it is a even parity. Only carry flag is set after this instruction. So these all are the arithmetic instruction for the today's lecture. In the next lecture we will be having the rotation instruction as well as the logical instructions. So let's guys deal with the questions on the today's session. So here is the first question on the today's session. Which one of the following addressing technique is not used in 8085 microprocessor? So there are the different types of addressing techniques we are using, which are register addressing mode, like one register. See, there are different instructions. Suppose move A comma B. So these instructions will be handled in the next class. So the contents of B will be moved to the accumulator. So this is register addressing mode. In the today's lecture we have said that immediate addressing mode. I also move MUI immediately 8-bit data, right? 8-bit data. So this is a 8-bit immediate addressing mode. This is the register addressing mode. This is immediate addressing mode, as well as register indirect, that is like from M, that is add M. So this is indirect. This is the contents of the memory only, but they are added indirectly by using this M. So this is the register indirect. So in 8085 microprocessor, register addressing mode is there, immediate addressing mode is there, register indirect addressing mode is there, but relative addressing mode is not used in 8085. It is instead used in 8086 microprocessor. In the 8086 microprocessor we have relative addressing mode. So for this question, D option is correct. So let's move to the next question, which is, due to add instruction, which of the following flags are affected? So see guys, this is a very simple instruction. I have explained you that due to add and subtraction are the simple operations, and due to these operations all the flags are affected. So for this question all the flags are affected, that is sign flag, zero flag, carry flag, auxiliary carry flag, as well as parity flag. All the flags will be affected after the add instruction. So let's move to the next question. What does ACI08H means? See, in the exam paper you may confuse this H. This H is nothing but the hexadecimal. It is showing that this 08 is in hexadecimal number representation, so you don't worry about this. So you know that this is addition with carry, this is immediate, this is 8-bit data. So just see what is the correct option. Option A is the correct option, because it will add 08 along with the carry to the accumulator immediately. It is a immediate. So A option is the correct. So let's move to the next question. In the next question, what is compare CMP R? CMP is compare the contents of the register R. Instruction will, what it will do is, the first option is correct itself, compare the data in the register R with accumulator. These are the wrong options. Complement, combine, compensate, these all are wrong words. Just be alert that CMP is compare. It just compares the data. According to that, flags are affected. Flags are affected, but register contents are not affected. Register contents are not affected. So this is the compare instruction. So let's move to the next instruction. What will be the content of accumulator after execution of the following instruction if it has 56H? It is given that accumulator has 56. The carry flag is set. Carry set is basically 1. This set is basically mean that 1. So carry flag is 1, and it is showing that SBB, subtract with borrow and 12. So this accumulator content will now become 56 minus, it has to subtract 12 from it, as well as it has to subtract borrow, which is nothing but in our case is carry, which is 1. So the result of this operation will be 43. So the contents of the accumulator after the execution of the following instruction will be 43. So option B is correct for this question. So let's move to the next question. What does DAA stands for? It is nothing but decimal adjust accumulator. It will just adjust the contents of the accumulator to a decimal value. So this is the DAA stands for. So let's move to the next instruction, which is how many T states are required for the execution of decrement M. See guys, for the execution of decrement B, that is if you are going to decrement the contents of B, it will require 4 T states because B register is within the memory, but here you are going to decrement the contents of the memory location. So here it is suppose written decrement M, so opcode fetch will be there, then it will going to read the contents of the memory location pointed by the register pair, which is 3051 suppose 20, then opcode fetch is there, memory read is there, then the data will be copied to the temp register. Here it is decremented by 1 immediately, and after that memory write is done. So 4 plus 3 plus 3, so it will require total 10 T states. So option C is correct for this question. So it will require 10 T states. So let's move to the next question. The next question is, due to instruction DCXB, which flags are affected? I have already told you that in the INR and DCR, carry flag not affected, all other flags are affected. Similarly in INX and DCX, whenever X is there, no flags affected. So for this, I guess option D is correct. So no flags are affected after the execution of DCX. So let's move to the next instruction. How many T states are required for the execution of add M? So let's check it out. So suppose here it is add M is there. So controller is here. So opcode fetch will be there as well as M. So it understood that it has to add the contents of memory location. Suppose our HL pair is here, which has 2050, and this 2050 has suppose 30. So it has to add the content 30 to the accumulator. So it will A plus 30. Opcode fetch is there as well as it will memory read. After reading this memory, this will come to the microprocessor. Microprocessor will now have accumulator as well as 30. So it will add it immediately to the accumulator and the result is stored. So 4 T states and 3 T states. So combinedly it will require 7 T states. So see guys, in this way you can easily understand how many T states are there. If your concepts are very good and if you easily understood the meaning of the instruction, how the memory is different from the microprocessor, you can easily understood how many T states it is going to require. So in this case it requires 7 T states. So let's move to the next question. INX RP instruction can't be used for the increment of. This is a simple question. You have to just remember the thing that it can be used for the increment of BC, DE, HL as well as SP, but it can't be used for the increment of program counter. See, no instruction can change the PC except no instruction like you cannot increment or decrement program counter. So INX RP works on stack pointer BC HL, but it does not work on the program counter. You have to remember this. So these all are the questions for the today's lecture. I hope you have liked the today's session. If you have any doubt regarding the today's section of arithmetic instructions, please comment in the video so that I will be answering the questions. If you have not subscribed to our GradeUp channel, I would like to say that please subscribe to our channel, please like this video, comment, and please share this video with your maximum of friends, because the microprocessor topic is very much important for this RRB JE exam, and it is very simple topic, but most of the students skip this because no one try to understand it or no one explain you very briefly. I guess I have did my best try to explain you. So I hope you have enjoyed this section. Try to comment on the video below. Thanks.